Hey everyone, so today we're going to be going over the question bits from the mentoring week 7 worksheet, which goes over a bit manipulation. So just to review, a bit is a number that represents, that is either like 0 or 1, where 0 is equal to false and 1 is equal to true. And a bit string is represented by a combination of like ones and zeros. An example of that would be right here, this is a bit string of 1001. And this would be, and each bit will be able to be like operated on separately and compared to separately. So let's compare some different like bit operators that we can use. So the first bit operator we can use is and what and checks is basically when comparing two bits, it checks if both bits are ones or if they're true, and if they're both true, it'll return 1. However, if either of the bits is 0, it will return a 0, representing that the overall condition is false. Another bit operator we use is or. Or takes in 2 bits, and then it checks if at least one of them is 1. If at least one of them is 1, it will return 1, indicating the condition is true. And if both of them are false, it will return 0, to represent that neither condition is met. And we also have XOR, which takes in 2 bits, and it checks if the bits are different. If the bits are both different values, so if it's either 0, 1 or 1, 0, it will return 1, indicating that they're different. But if they're both the same, it will return 0, indicating that both values are equal. And then next we have not, which only takes in 1 bit, and it basically just negates a bit. So basically, if we put in 0, it'll return 1, and if we put in 1, it'll return 0. And next we have left shift. And what left shift does is moves a bit to the left. Basically, what that means is it's taking the bit string and it's adding a 0 to the right. So I think the best way to show is by drawing another box up here. And then let's try shifting left the value 0 or 1, 0, 0, 1. And then in order to do that, we would move 1 to this second box here, the second most least significant, 0 to box here, and then 0 to box here. And then we would have add a 0 here to fill in this gap, and the 1, the most significant, would be discarded because of the lack of room. So that's how you shift a bit string left. And then we can do another thing we do is arithmetic right, which basically instead of moving everything to the left, it moves everything to the right, and then it copies whatever the leftmost sign bit is to the new number. So if we do a right shift on this number, let me draw a box. I'll do 1 move here, 0 move here, 0 move here, and it'll copy this value to be over here. So if this value since this value is 0, we add a 0 to the front. But if it was 1, we'd add a 1 to the front. And logical right would operate the same way. We're also moving each bit to right. But the only difference in behavior is that instead of copying the most significant bit from here to the new value, it'll just automatically fill this in with a 0. There's no big difference here, but if we were shifting this original value, like 1, 0, 0, 1, we would shift it to be 0, 0, 1. And then if it was an arithmetic right shift, it would be a 1. If it was a logical right shift, it would be a 0. So hopefully that makes sense. Yeah, so now that we know the different symbols that we can use, let's move on to the first question. So the first question states that X is a single bit input, which means it's 1 bit, so it's either a 0 or a 1. And then we're going to go through the following operations and fill in whether the resulting value will be a 0, or if it's a 1, or if it's X. So basically, it's just depending on whatever the X variable we put in is, or if it's not X. So let's look at the first one. So we're doing X and 1. As recall from before, and only returns 1 if both bits are 1. So if X was equal to 0, then it will return 0 because there's at least 1 0 in the mix. If x is equal to 1, however, it'll be a 1 and 1, and that would result in a 1. So as a result, this operation would return a different value depending on what x is. So, and that returns a different value based on what x is, or like if it's equal to x. So the answer to this would be x, because it returns a 0 if x is 0 and 1 if x is 1. So let's move to the next one where we're doing x and 0. As we recall from before, we need 2 1s in order for and to return true. However, we're already given 1 0 or 1 false, and so it's impossible for this and to return a true or 1, regardless of what x is. So we know we can fill this in with 0, because we know the condition to return a 1 is not met. And next we're doing x and x. So we're basically anding the x with itself. So if x is equal to 0, we're doing 0 and 0, and this would return a 0. And if we're doing if x is equal to 1, we're doing 1 and 1, which would return a 1 because they're both true. So as a result, we see this is also dependent on what x is, and so that's what our output is. So next we're going to do x or 0. And if we recall before, or only requires at least one of the numbers to be a 1. So in this case, if x is equal to 0, then it'll be 0 or 0, which returns 0 because there's no 1s. And if x is equal to 1, it will return 1 and 0, which is equal to 1 because there's at least one true value in the mix. So as a result, we see this is also dependent on what x is, so this returned x. The next thing we're doing is x or 1. And if we think about this, or only requires at least one true bit or one bit. And we see we're already given one bit. So it doesn't matter what x is. So x could be 0 or 1, and it will always return 1 because we're already given one true. And next we have x or x. So we're doing or on itself. So if x, or if we do x for x and x is 0, it'll be 0 or 0, and there's no true, so it'll be return a 0. If x equals to 1, it'll be 1 or 1, which will return a 1. And so this is dependent on what x is. And now let's move on to x or 1, or x or 1. So if we recall from before, XOR checks if the two bits are different. If they're different, it will say 1. If they're the same, it'll say 0. So if we do x XOR 1, we would do, and x is equal to 0, it will be x XOR 1, which, and 0 and 1 are different, so we'll return a 1. And then if x is equal to 1, it'll do 1 XOR 1, 1 and 1 are the same, it'll do 0. So we can see this, the output also depends on x, but it's always the opposite of x. If x is 0, it will turn a 1. If x is 1, it will turn a 0. So the output would be negation of x or not x. Let's move on to x XOR 0. And then we put an x equals 0 into this, and x 0 XOR 0 will return 0 because they're the same value, and x equals 1. 1 XOR 0 would equal 1 because they're different values. And so we see this is entirely dependent on what x is. And if we do x XOR x, we're doing carrying x to itself. The thing is, we're comparing x, since we're comparing x to itself, we're comparing the same variable twice. So it's impossible for there to be any difference between the two variables because we're comparing the exact same thing. So we know this will always be 0 because there's never any difference between itself. Yeah, so that's basically how you would do the bitwise comparisons using ands and ors and XORs. So let's move on to the second part of the problem, where we're going over different functions and explaining what a function does. So for the first function, we take in an input n, which is an n-bit number. And just to recall what that means is n is equal to has eight digits. And these digits have either can take out the value of 0 or 1. And in order to simplify it, to make this more like hands-on or like easy to understand, I'll just fill in like dummy variables inside each OP. I'll say this is n0, n1, n2, n3, and then so on. So let's take a look at this function. So the first thing we do is create R, a random object. And then we call, we left shift 1 by r.nextInt7. So basically what with that function is returning a random number 0 to 6, or like random integer 0 to 6 inclusive. And then it's shifting 1 by that number. So let's say r.nextInt7 returns 3. It'll basically be, I'll turn 1, it'll shift it by 3, so it'll become 1, 0, 0, 0. So 1 would be shifted by the random value generated by like r.nextInt7. And then since we're comparing with an 8-bit number, we just fill in the remaining bits in front of it with zeros. So if there's like, if we shift by 3, in this example, we'd add 4 zeros in front of it. So let's do this comparison. So let's pretend this is the value of b we got, and then we want to XOR it with n. So it'll be a row of zeros until a 1 1 at the rth bit, and then we'll have more zeros. And recall from what we figured out before, any number XOR 0 will result in our original number. So if we do the first bit XOR 0, it would also be first bit, second bit XOR 0, the second bit, and then we go on through the whole thing. Except the only difference is when we rise to a bit XOR 1. And when we XOR a bit with 1, it automatically returns a like not of the bit. So if the bit was 1 originally, it will return 0, and if it was 0 originally, it will change it to 1. So now we have the rth bit will change to its opposite, and then the other bits will stay the same. So what we're figuring out from this function is it'll take in the number n, and it'll return the same number except for some whatever random number in generated, it'll change that to its opposite. So if, let's say, n was 0, 1, 0, 1, 0, 1, 0, 1 originally, it'll return the same value, except it'll change whatever rth bit was, in this case 3, will change this to 1. So yeah, that's what mystery function 1 does. So let's look at mystery function 1, 1. So it does the same first few steps. It takes in a random number r, and then also it uses that r to generate an integer between 0 and 6, and shift 1 by that number. And then we set the number to an integer b, and then we do n and not b. So in this case, we want to think about what's happening to b here. So the first thing we want to do is we want to find the not of b. So we've established for b is the same value of b as before. So it's also 1 followed by a bunch of zeros and preceded by a bunch of zeros. So the opposite of that would just be would be a 0 preceded by a bunch of 1s and followed by a bunch of 1s. So if we go back to our example of x equals, or like r equals 3, it'll just be a 0, and then it'll be 4 1s before and 3 1s afterward. So that's what not b would look like. And then we want to do an and with n. And so what we recall from and operations is that and will only return 1 if both numbers are 1, and it will return 0 elsewise. So since we have a bunch of ones, it'll it'll change the bit to a 0, set the bit to 0 or 1 is really dependent on whether what n is. So since like if we look at the leftmost bit is a 1, and we'll just compare it to n leftmost bit. So the result would just be whatever n n's leftmost bit would be, because that's the determining factor of whether it's n returns true or not. And then so it'll do this for every single value except when we reach 0. When we reach 0, it'll automatically set whatever value it is to 0, and then it'll continue to save for the rest of the behavior function. So we know the behavior of this function is it's basically taking the original 8-bit number n, and it returns like almost the exact same thing. It changes like everything is the same except at some like random like digit rth digit, it will change that value to a 0 regardless of what it was originally. Okay, so let's move on to the mystery function 2, and it also takes in the 8-bit number n, and we're returning n or 0 1 0 1 0 1. Okay, so what we know about OR is that it'll return 1 as long as at least one of the values is 1. So when we're ORing any number with a 1, it'll always return 1. So let's look at the static number they gave us. So the static number gave us has a 1 in every other position. So we know this position will be 1, this position will be 1, this position will be 1, and this position will be 1. So we have 4 guaranteed 1s. And then the rest of them are ORs with 0. So if we're doing a number or 0, we want to, the result is really dependent on what the original number is or what n is. So if like n was 1, it'll return 1. If n was 0, it'll return 0. So since it's dependent on n, I'll fill in the n variable. So it'll be like n0, n2. So I'm just writing this in to show it's dependent on what n was originally. So yeah, so now we know that mystery function 2 will basically take in n. It will return n except every number is guaranteed to be set to 1 if it wasn't originally, and they'll set in and the even numbers will be set to remain the same as the original. Yeah, so that's how mystery function 2 is, and let's go to the next page for the last function, mystery function 3. So mystery function 3 is a bit different, as in it takes in 2 variables, to x and y. And let's see what it's doing here. So the first thing is that it reassigns x to be equal to x, or y. So the best way to do that is to draw out. So we have x, and it's setting it equal to x, or y. And then we want to do, and then y is still equal to y at this point. So let's move to the next line. So and next time we're reassigning y to be equal to x, or y. So x is still equal to x, or y, because that's what we are not reassigning it in this line. We already assigned it before, and we're altering y this time. So we're doing y is equal to x, or y. The thing is, we previously assigned x to be equal to x, or y. So it will be x, or y, or y. And the thing is, XORs are commutative. So we could replace the parentheses around x, or y to be around y, x, or y. So it'll be like, we can do this operation first. And we previously established that any number XOR itself will always return 0. So we can replace y, or y with 0. So it'll be x, or 0. And we also established that any a number XOR 0 will be equal to itself. So x, or 0 will be equivalent to x. So basically what we're doing here is after this line, the y will be equal to x. And then we go to the final line, we see we're altering the assignment of x again, and we're setting it to x, or y. So what's happening here is we're taking the value of x, which we established, which is x, or y, and we're XORing with y, which we assign to x. So right now we have x, or y, or x, And we can use the commutative property to move the values around. So we can change it to x, x or y, and put the evaluate x or x first. And then if we do x or x, we have that return 0 because we're XORing a number with itself, and we're doing 0 XOR. So we're doing x0 XOR y. Any number x or 0 return itself, so 0 XOR y would become y. So and then y will still be equal to x as established before. So what we're seeing in this function is that it's swapping the values of x and y. So y is becoming x and x is becoming y. Yeah, so that leads to the end of this problem. I understand bit manipulation can be a bit tricky, but hopefully this clarified things a bit. No pun intended. Right. Thank you for watching.